this lecture we talk about proof systems. So instead of talking about validity, we want to talk about proofs. We want to talk about proofs. Okay. So what is a proof, and what is a proof system? Proof system consists of two things. One is axioms. So these are things that we agree are kind of true or proved without, because these are the axioms are things that we agree that we consider as proof, already proved. And inference rules. So what are inference rule? Allows us to extend the proof with a new formula. Okay, so let's take an example. I mean, an axiom that we might want to use is something like for all alpha or not alpha. This might be an axiom that we might put in our proof system. Okay, we know that this is a valid axiom. Okay, an inference rule, an example of an inference rule would be something like this. So inference rule consists of two things. This is a precondition. So these preconditions consist of things that we have already proved and the conclusion. So let's see an example. So one very famous example is, so suppose you have alpha. From this you can conclude alpha or beta. Okay, so this you should read it as, suppose I have proved alpha to you, then I can extend it to a proof of alpha or beta. Okay, so once we have such a proof system, so once we have a proof system, then a proof under a proof system let me call it, say, P, is a sequence of formula C1 Cn, okay, such that each Ci has the property that either Ci is an axiom or Ci is the conclusion of an inference rule. It's a conclusion of an inference rule in P whose precondition are already present in C1 through Ci minus 1. So somewhere in the previous statements, so you have these things that you agree is a proof. You can add Ci if it follows from an inference rule from some previous elements. Okay, that's what proof is all about. Okay, so one point that we want to say is axiom can be seen as an inference rule with no precondition. Okay, so which means that you can just write this, okay, to mean that alpha is an axiom. Okay. Okay. So before we go into a particular proof system, let's talk about some of the things about it. So let P be a proof system. Then we have this notation. We say if there exists a proof C1 Cn using the proof system P such that Cn is C. So you have a proof of, or other words, one can prove C using the proof system P. Okay, so compare this with this, which semantically means C is a valid. Okay, so a proof system can be used to prove things, and but we need to talk about, I mean, one of the things that we do is we talk about proof systems, we study proof systems in logic. So note that we will suppress the subscript and subscript P in this. So we will just write this to mean when P is understood. By the context. We most probably will be talking about one particular proof system, and in that context we will skip this subscript. P is or C is suggestive of this. Okay. Okay, so here we are saying C is valid, and here we are saying C is provable in some proof system. P, but let's say for time being say that there is some fixed proof system. Okay, we'll look at examples of proof system later on. So let's look at this comparison. So so here is validity semantic semantically valid, and here is provable. So the notation that we had here is this to say that C is true and is valid, and here we have this. Okay, now we had a notation as follows. So what did this mean? Recall that this meant C is so this one means phi is true whenever gamma is true. Okay, or for all worlds V in models of V proves C is valid in proof. Similarly, we have this notation gamma. So what is this? So here we say that if there is a gamma proof for C, okay, which means that in the proof of C you can use the set gamma as axioms. Okay, so the proof system comes with an axiom, so typically under some proof system. So P union gamma. Okay, so this is equivalent to just gamma. Okay. So yeah, one thing that you can notice here is gamma, then there exists a finite set subset gamma naught subset of gamma such that gamma naught proves phi. So this is easy to see. Look at a proof. So, look at a proof C1 Cn equal to phi in P union gamma. So take the axiom system to also contain gamma. There are, since the proof is finite, since the proof is a finite sequence, okay, only finitely many elements of gamma would be used in it. Gamma 0 is that finite subset.